Welcome to the third video on torsion in circular bars. In this video, we'll finish finding the polar moment of inertia, J, which will allow us to determine the two elastic torsion equations. This is therefore our distribution of shear stress. Now, from this distribution of stress, we can obtain the moment induced by an element under this stress distribution. The element caused by this is going to be, the torsion caused by that, dt. That's going to be equal to, well, the shear stress the element's under times the distance from the centroid times the area of the element. Well, the area in this case is a differential area with respect to, well, it's just a differential area. So, if we want to know the total torsion, we can just integrate over the full area. Torsion caused by this stress distribution is going to be the integral of the shear stress times the distance with respect to A. Now, fortunately, we just found out how to get our shear stress right here as a function of our distance from the centroid, right? Let's use the fact that the shear stress is going to be equal to rho, our distance from the centroid, times whatever the maximum is of shear stress, divided by the maximum distance here. This distance right here is c, right? Any more than that, and there is no stress because you're out of the rod, and air is not going to be holding shear stress for you. Alright? So, if we pop that in for there, we're ending up with something a little bit more palatable looking, which is to say that we're getting that the torsion is equal to, let's put these on the outside. Yeah, they're constants. Whatever the maximum shear stress is, divided by C, times the integral of rho squared over the full area. But of course, we're still integrating over the area, which is not great. Optimally, we'd only integrate with respect to one distance, and that would be with respect to rho. So how can we get the area with respect to rho? Well, it's a circle. So if we're looking at an element, it's going to be equal to our distance in the rho direction times the circumference, which is going to be 2 times pi, right? For our, I don't know if you can tell, this is, okay, fine. The drawing wasn't great. It should look more like this. Oh dear. If this is our element, then its area is going to be the area in this direction, our differential distance in rho, our rho direction, times 2 times pi times rho. So we can turn this into, or we can turn this into the same thing over c integral rho squared times 2 pi rho, and then just differentiate with, or integrate, excuse me, with respect to rho. Turns out pi is a constant, as is 2. So let's write this all down on the outside, make the integral as easy as possible. Also, not forget to write a max right there. So that's all together. It's going to be the maximum shear stress experienced divided by the maximum radius, or the outer radius, of the bar, times 2 times pi times the integral of rho cubed, and that's integrated with respect to rho. Presumably all of you can do that pretty much in your sleep. This constant, the max is safe. The maximum radius, that's all still there. Pi over 2 times, well, we're gonna be integrating from 0 to c, right? So that's gonna be c to the 4th. Now, this value right here that I'm bracketing right here, and I guess I'll just write it right here, that it equals the maximum shear stress over the outer radius is known as the polar moment of inertia, J. Okay, and its units are, of course, going to be length to the 4th. It fulfills much the same role that the second moment of inertia does when we're doing bending, but for torsion. All right, so let's think about the only other situation that we'll consider in this class right now, which is hollow cross sections. If we have that, what's going to happen? Well, that means that this center bit is not going to be present, but we're not going to start the shear stress at 0 out here. It's going to start at whatever it is up here because, well, it is rotating, right? We got that from the strain distribution. The strain distribution isn't going to change. It's just not going to be affecting anything in here. So the stress distribution, that remains, which means all of this is still valid. We're just going to integrate from different points. Right, so instead of integrating from 0 to c, we're going to be integrating from c1, say, to c2. And the result of this is we're going to get exactly all the same stuff, except we can write down a more general case of our polar moment, J, which is that it is going to be equal to pi divided by 2, that part's safe, times the outer radius to the 4th minus the inner radius also to the 4th. So this is going to be used rather frequently. And with this, we can now write down some pretty, go back through into here and get our maximum shear stress as a function of J and C and T, right? Because we are able to now write that T, the total torque that we're applying, is going to be equal to the maximum shear stress we're experiencing divided by the outer radius, that's what that is right there, times J, which we're able to find pretty easily. And we can rearrange this now to give us the shear stress at any given point as we move out from inner. Obviously, it'll be 0 at the center, and it will be its maximum at rho is equal to C. So that's going to give us that the shear stress as we progress outward is going to be, well, T times our distance from the centroid divided by J, our polar moment of inertia. These are our elastic torsion formulas, and so as long as we are in the linear elastic region, we can use them, and as long as we're dealing with circular shafts, be they solid or hollow, these are valid to use. Let's look at an example next.